Okay, first of all, thank you for having me invited to this event and for the possibility to speak. And of course, happy birthday, Boris. So the talk will be very marginally linked to optimization. So, and it will be largely purely mathematical. And what it's about.
And you mean that optimization has nothing to do with
So you will see what I mean by mathematical. So, actually, in the last several years, it appeared that while optimization was moving from its realm into geometry, at the same time, there were some people in geometry that were moving towards optimization and found results that are relevant for optimization, but from their geometric point. And what I want to present today is some, geometric points of view on barriers on three-dimensional cones. Okay, so first some introduction, which is probably very familiar. So regular convex cone. And over such cones, we can define conic programs, which are just problems of minimization of linear functions over an intersection of the cone with an affine subspace. So actually, if you have any convex optimization problem, you can homogenize the convex set and you get a conic program. So this is a very general class of problems. And of course, the complexity of this problem depends on the complexity of this cone here. Okay, so there is a class of methods for solving conic programs, which is called interior point methods. And these interior point methods rely on so-called barriers on these cones, which are essentially penalty functions that penalize if you move out of the cone. And these barriers have to meet some criteria. So for conic programs, for if the underlying set is a cone, the barrier is assumed to be logarithmically homogeneous. That means if you multiply the argument with some constant, then the barrier gets an additive correction with some coefficient nu here, which is called a self-concordance parameter. Then, of course, the penalty moves to infinity if you move to the boundary of the cone. It has to be convex. And it fulfills a so-called self-concordance condition, which bounds the third derivative of the barrier in terms of the second one. So we see, there are two objects that will be relevant for this talk. This is the second derivative of the barrier, which defines a Riemann metric on the interior of the cone. And it's the third derivative, which can be seen as a cubic tensor, a cubic totally symmetric tensor, which is bounded in terms of the metric. And if we have such an object on the cone, which is computable, so you know how to compute gradient Hessian, then you can devise a method to solve general conic programs over this cone. And these methods go like this. So you have your cost function. And to this cost function, you add the penalization, and then you solve the unconstrained convex optimization problem, which gives you a solution in the interior of the cone. But if you increase the weight of your original cost function, then the solution will move to the boundary of the cone, following the so-called central path, and converge to the optimal solution of the original problem. So this is conceptually very simple, and as usual, the complexity hinges on the presence or on the availability of such a barrier function. Okay, and this parameter here, this factor, determines the speed of convergence of the solution of this unconstrained problem to the solution of the constrained original problem. And here the smaller this parameter, the faster is the convergence. So you want to have barriers with parameters as small as possible. Okay, so if we are given a cone, then it's natural to ask what is the minimal self-concordance parameter which we can achieve on this cone. And there are a lot of results on this. So the first result, due to Nesterov and Nemirovsky, was that essentially the minimal self-concordance parameter has to be at most of the order of the dimension of the cone. So, and actually this can be proven by presenting a barrier, a concrete barrier, the so-called universal barrier, which has this bound on the concordance parameter. So, and this constant here could be computed, but it was in the order of several hundreds, I guess. Okay, so then there has been another barrier, the so-called canonical barrier, which gets rid actually of this constant here. So the canonical barrier has a concordance parameter which is bounded by the dimension of the cone. And a funny thing about this is that it was found essentially simultaneously by an optimizator and a geometer. So, and very recently there has been discovered a third barrier, the so-called entropic barrier, which has also parameter n plus correction of smaller order. And it turns out that it's actually not so easy to compute the exact value of this optimal parameter, but for a class of cones, the homogeneous cones, it has been done almost 20 years ago, and this depends on the construction of these cones, on the Weinberg classification and on the corresponding construction. And here this optimal parameter equals the so-called Siegel rank of the cone. And these are upper bounds which are proven just by presenting a barrier, but one can prove also lower bounds. So for instance, if the cone has an extreme ray which locally is like an extreme ray of the simplicial cone, then the barrier has to be at least the dimension of the cone, and this means it has to be equal. The optimal barrier has to be equal to the dimension of the cone. Okay, so if we have a cone and a barrier on it, and we look at our conditions here, we see that if this third derivative is small, and this inequality here is not achieved, then we can multiply the function f, the barrier, by a constant smaller than 1 and decrease this self-concordance parameter without violating this inequality. So what one can do a priori is to assume actually that equality holds here. And we will call such barriers minimal. So for a given barrier, we multiply it by a constant as small as possible to achieve equality, and that will be the corresponding minimal barrier. But it does need not to be optimal, because we may have another one which is not proportional, which is a lower concordance parameter. Okay, so now we come to the structure of the Riemann metric. The second derivative defines a Riemann metric on the interior of the cone, and the interior of the cone has a natural foliation. So, and on the one hand, we can foliate this interior into level surfaces of the barrier. So the barrier is just a scalar function, so it has level surfaces. And on the other hand, we can foliate the interior into the set of rays. And these two foliations are, well, transversal. So the interior of the cone is just a direct product between a level surface and a ray. And it turns out that it's not only topologically like this, but also the Riemann structure is a direct product of the Riemann metric on the level surface and on the ray. So the Riemann metric factors out a one-dimensional trivial factor, and all the non-trivial content is inside a level surface. So we may consider, instead of considering the interior of the cone, just a level surface and work with the level surface. So this decreases the dimension by 1. And this is where geometry sets in. So if we have an affine space, so in our case it's just Rn, and we have a hypersurface in this space, then this hypersurface defines two objects. It defines the so-called centro-affine metric, and it defines so-called cubic form. So where the centro-affine metric is just a metric on the surface, and the cubic form is a totally symmetric 3 tensor. And it turns out that the metric H, the centro-affine metric, is just proportional to the second derivative of the corresponding barrier, and the cubic form is proportional to the third derivative. So we might consider this pair of metric and cubic form just as the pair of second and third derivative of the barrier. These are equivalent objects. And then a quite deep theorem in differential geometry says, if we have a surface, so not embedded in some space, but just a manifold, and on this manifold we have a metric and a 3 tensor which satisfy some compatibility requirements, then we can recover the immersion of the surface into an ambient space, and from this immersion we can recover actually the cone and the barrier on the cone. So these two objects here, if they satisfy some additional conditions, can be viewed as an equivalent description of the cone together with the barrier on the cone. And then if we consider 3-dimensional cones, the level surfaces are 2-dimensional surfaces. And what is a 2-dimensional Riemann space? It's a Riemann surface. So it's a well-known object from the 19th century. And it defines a so-called conformal structure. So what is a conformal structure? It's just a metric which is defined up to conformal transformations. That means up to scalar multiplication of the metric where the scalar depends on the point. And there exists a strong result which describes all these Riemann surfaces. So this is the uniformization theorem. And it actually says that every simply connected Riemann surface is conformally equivalent to one of three standard spaces. So either the unit disk in a complex plane equipped with the hyperbolic metric, so just hyperbolic space, or the complex plane itself equipped with the flat metric, or the Riemann sphere equipped with its usual positive curved metric. This theorem has been proven for quite a while, but I guess in the form that is used today, a complete proof has been given in 1907 by Koeber and Poincaré. Okay, so this uniformization theorem, if we are given our Riemann surface equipped with the metric, says that we can choose a coordinate system such that the metric becomes proportional to the, well, at each point to the identity matrix. So it can be written in this way. And then we can introduce a complex coordinate on this two-dimensional manifold, and the metric will look like this. And moreover, we can choose a global chart where this complex coordinate takes values either in the unit disk or in the complex plane or in the Riemann sphere. And for our case, the Riemann sphere actually does not happen because the Riemann sphere is compact and the level surfaces of our barriers are not compact, so they cannot be conformally isomorphic. So there exist only two possibilities. Either the level surface is conformally equivalent to the hyperbolic space or to the parabolic or flat space. So this was the metric. And now we come to the cubic form. So the cubic form is a symmetric 3 tensor, and in 2 dimensions it has 4 components. So here I've written, actually it has 8 components, but 4 of these are linearly independent. And if you have Euclidean space and you have a quadratic form and you consider orthogonal transformations, then this quadratic form can be split into a trace part, which is proportional to the unit, to the identity matrix, and in a trace-free part. And the same happens for higher order tensors, so they can be split in a trace part, which is proportional to the metric in some sense, so this is the red one, and in a trace-free part, which is the blue one. And for 3 tensors in 2-dimensional space, it turns out that both parts have dimension 2. So of the 4 independent components, 2 are determined by the trace part and 2 are determined by the trace-free part. And if you write this cubic form in this form, so in these 4 variables instead of the usual components, and you compactify the trace-free part into this complex variable here, then you can write the compatibility requirements between the cubic form and the metric like this. So it's not very important how it looks like in detail, but there is one special case where the trace part vanishes identically, and then you see that this the trace part is the gradient of some scalar t, so this vanishes, and if this E vanishes, then what remains is just that the trace-free part U is a holomorphic function, and this holomorphic function, its modulus is given by some function of the metric. And it's exactly this case where which corresponds to the canonical barrier. So the canonical barrier is characterized by the condition that the trace part vanishes, and then automatically the trace-free part is given by a holomorphic function. So for the canonical barrier, the description of the cone plus the barrier is a pair which is composed of a metric on the surface and of a holomorphic function on the surface. And then it's interesting to see what the correspondence is. So you can give the cone and the barrier, but you may also give the metric and the holomorphic function and then ask yourself, well, what is the cone which corresponds to this pair? And what is the barrier parameter? And it turns out that, well, the compatibility requirement is just that this holomorphic function has a modulus which is given by, this is proportion to the metric, and this is the curvature of the surface which is defined by the metric. And if this compatibility requirement is met, then the pair defines a cone and the canonical barrier on it. And moreover, we may also just we may also just postulate the metric, and then if the metric satisfies a compatibility requirement on its curvature, then there exists one parametric solution, family of solutions for the cubic form, which defines one parametric solution, or one parametric family of cones. So each metric corresponds to a one parametric family of cones. Okay, so this is, I will skip this. And here comes the mathematical part. So these are the examples. So quite recently, this is almost a book, so the proof is very long. If this holomorphic function is a polynomial, then the corresponding cone will be polyhedral. And the degree of the polynomial is the number of rays of the polyhedral cone minus 3. So for instance, if this holomorphic function is just a constant, then you get the simplicial cone, so the positive orthant. Then there exists an interesting example on compact surfaces. So you might ask what compact surfaces have to do with the level functions. But if you have a compact Riemann surface, you can always consider the universal cover. And the universal cover will be the level surface. So a compact Riemann surface has a symmetry group, which is the fundamental group. And this symmetry group will also translate to the universal cover. And in this way, you can construct cones which have a discrete symmetry group with a so-called co-compact action. So the quotient of the cone with respect to this group is compact. And this gives you cones which can be tiled like this. So probably everybody has seen a picture like this. This is a tiling of the hyperbolic disk by some Fuchsian group. So the cone will be divided into polyhedral cones like this, and the union of these polyhedral cones will make up the whole cone, but in general it will be not smooth, so it will be C1 but nowhere C2, the boundary of the cone. And also last year there appeared a result which links the curvature of the cone to a lot of conditions on the metric. So if the curvature of the Riemann surface is bounded away from 0, then it's equivalent to the condition that the geodesic triangles have bounded width, so they have not infinite size. It's equivalent to the condition that the corresponding cone, if you act with the special linear group on the cone and consider the closure of the orbit under this action, that this closure does not contain the orthant, or that the Riemann surface is conformally equivalent to the hyperbolic disk and the cubic form is bounded in terms of the hyperbolic metric, or that the boundary of the cone is quasi-symmetric. So this is a quite simple condition, but it's technically a bit involved. And with this result, you can actually characterize all three-dimensional cones where the optimal baroparameter equals 3. So in order to do this, we need a result that links the norm of the cubic form to this self-concordance parameter. And this is given by this formula, so the details are not very important. But what is important is that the higher the curvature of the Riemann surface is, the higher will be the baroparameter. So the supremum of the curvature will define you the baroparameter, and this formula has a graph like this. So if the curvature is identically -1, so this is the hyperbolic disk, then the baroparameter will have its lowest value 2. If the curvature is identical to 0, which is the flat space, then the baroparameter will equal to its highest value 3. And this corresponds, of course, to the simplicial cone and to the Lorentz cone. Okay, so we then get a characterization of all three-dimensional cones which have an optimal baroparameter equal to 3. So these are exactly those cones such that if you act on them with a special linear group, the orthant is in the closure of this action. So you find a sequence of linear transformations such that the images of the cone under these transformations tend to the orthant. So if and only if this happens, the optimal baroparameter is 3. If not, then it's smaller than 3, and then you get all these equivalent conditions which have been proven here by Benoit and Hulin. So all cones, all three-dimensional cones with optimal baroparameter smaller than 3 are characterized by these equivalent conditions. So the geodesic triangles have a finite width. The canonical barrier has a parameter smaller than 3, or the level surface is conformally equivalent to the disk and the cubic form is bounded, or the boundary is quasi-symmetric. And moreover, there is a bijective correspondence between the isomorphism classes of these cones and the isomorphism classes of bounded holomorphic functions on the hyperbolic disk. Okay, so this is for three-dimensional cones. Of course, you can ask the same question, or what is the generalization for n-dimensional cones, and what is the optimal barrier parameter if you have this case? So it can be anything between 2 and 3. And you might ask when a barrier is conformally equivalent to D, when it is conformally equivalent to C. So that's, for mathematicians, it's open playground. Okay, so thank you very much.
So, any question? Remark?
Yes. You use the third derivative in the conditions. And what happens if it does not exist? Can it be replaced?
So it's an axiom. So for the barrier, a function is a barrier if the third derivative exists. So it's you ask for, you consider only smooth functions.
Are there exceptions for not so smooth functions?
Well, I mean, the interior point methods do not use explicitly the third derivative. They use only the Hessian. So you might run the algorithm also with a function where the third derivative does not exist. But I guess that all the theorems will not be valid. So the convergence will not be guaranteed.
Just a small question, because you see during many years some people were convinced that the barrier parameter should be integer. At least in all of these examples which are applied in practice, we have only integer parameters of the barrier. And now you have examples of the barrier for which the optimum parameter is fraction.
Exactly, yes. So it's 2 only for the Lorentz cone. If it's not the Lorentz cone, it can be 2. So if it's not 3 and not 2, the 3-dimensional cone has to have an optimal fractional parameter, yes.
Okay. And all of that can be applied if we want to 2-dimensional sets.
To 2-dimensional level surfaces.
No, we just intersect cone, so we have intersection 3-dimensional cone. We get 2-dimensional sets, and for the dimensional sets we have just consequences. The same consequences from your theory.
So, of course, if you have an n-dimensional cone and you have the optimal barrier on it and you intersect, then the restriction of the barrier to the intersection...
You don't intersect like this, you intersect orthogonally.
So yes, compact affine section.
Yes.
So, yeah, I mean, the optimal barrier on the cone might not give the optimal barrier on the section.
But
So
it looks like that you should be able to apply the same technique, because essentially it is more or less the same objects, 2-dimensional set and 3-dimensional cone.
well, if you have a compact set, then the level surfaces will be topologically equivalent to a sphere, right? And there exists a theorem that says the equivalent of the canonical barrier for a surface which is even in n dimensions, which is topologically equivalent to a sphere, can exist only if it's an ellipsoid, if the surface is an ellipsoid. So all this will work only if your original set is an ellipsoid. And then everything is trivial. I mean,
Other questions?